being doing that. Sorry.
We all set? All right. So today we're going to do Chern-Simons Theory for finite groups. The reference for this is Fried-Quinn's paper, Chern-Simons Theory with Finite Gauge Group. So for today, G is going to denote a finite group, and we're going to be looking at principal G bundles over some space X. And note, since G acts transitively and is finite, P is a finite and regular cover of X. So your usual covering space theory will hold. Let's talk about the classical theory first. So this is kind of what we've been talking about for the past couple weeks, but now in the case where we've got a finite group. So the basic data needed to define a Lagrangian classical field theory are, well, one, we need a space of fields for every space-time, so every manifold, and an action functional. And this is supposed to map from the space of fields over X into R. Well, sort of. We saw was R mod Z valued for classical Chern-Simons. So for the classical Chern-Simons we've been talking about for the past couple of weeks, our space of fields has been principal G bundles over X with this extra data of a connection. And the action functional was, well, it was integrating this pullback of the Chern-Simons form that we associated to the connection. And this was, well, I guess, R mod Z valued. And this data allowed us to define TQFT from Bordism, well, 2-3 Bordisms with this data of a connection into, well, I guess it was complex one-dimensional inner product spaces with the usual functoriality, orientation, additivity properties, and gluing as well. So now in the case where we have a finite group, our Lie algebra is zero-dimensional, so there's only one unique connection. For any bundle. So this extra decoration of having a connection over our principal G bundles can be omitted to define this TQFT. And so the classical construction gives us a TQFT now from board 2-3 with just the data of a G bundle over our 2 or 3 manifold into complex lines. And just to fix notation, I'm going to note this as well. Closed-oriented 2 manifolds with a bundle go to some line LQ, and morphisms will go to this element given by the action functional. And this is valued in L of the line associated with the boundary, Okay, why is this a TQFT? Use your functoriality orientation and inner products here to identify this with a homomorphism between those two lines. Okay, and this has the usual functoriality orientation gluing properties. So some remarks about this classical theory. Well, if we were to proceed using the usual construction that we've been talking about the past couple of weeks for these principal G bundles for a finite group, pretty much everything becomes 0 and this TQFT becomes trivial. I'll talk about what that means exactly later on. So in this Fried-Quinn paper, we generalize this this construction, and I'm not going to go through the whole details because I want to get to the quantized theory. But basically how it works is, well, okay, so fix your finite group. And, well, okay, this is also generalized to arbitrary dimensions. But to define this new theory, we're going to also need to fix a cocycle in the d+1 chain of the classifying space for G valued in R mod Z. And the theory we get is going to depend on the choice of this cocycle. And anyways, the generalized classical theory gives us a TQFT now from Bordisms of D to d+1 manifolds with this data of a G bundle into complex lines. Let's see, so I'm not going to spell this out exactly, but for closed and oriented manifolds Y, our LQ now is going to be invariant sections of some functor associated to any G bundle over Y. And it also depends on the choice of this cocycle, alpha hat. Recall Val defined invariant sections last week. I'll give the definition again later on. It's not super important what it is now. We just need to know that we associate some line to any D or closed-oriented D manifold. And for d+1 manifolds, compact and oriented, we get an element of this line associated to the boundary. And this is purely notational. S of xp is not actually an element of R mod Z, except in the case where x is closed. This is kind of just to denote that this is actually going to be unit norm. Some remarks. This functional actually depends only on the cohomology class associated with this cocycle. As I said, when our d+1 manifold is closed, this action functional is going to be valued in R mod Z. And the third thing I want to say is that, well, if we look at this theory in the untwisted case, That is, when alpha hat equals 0, the theory becomes trivial. What do I mean by that? Well, we get canonical trivializations of these lines, and this element just becomes the identity under these trivializations. So that's the classical theory that we get for these choices of a group, cocycle, and dimension. And from it we get a TQFT like before, but from Bordisms from D to D plus 1 manifolds with the usual functoriality, orientation, additivity, and gluing properties. So now that we have that, I want to talk about the quantum theory.
So can I just ask, what's the interpretation of this cocycle? How mapping with it?
I don't really have a good geometric idea for how to think of it. It really comes up like very fundamentally in constructing this functor. I mean, I could.
You don't
yeah.
go into like super details, but just if there was a way of thinking about it, then that would be cool. If not, then there's not.
Yeah, I'm not exactly sure. I haven't worked out enough examples per se to know how it interacts. I mean, this is kind of the only intuition I have for it at the moment.
If I restrict to d equals 2,
Mm-hmm.
do I get the whole thing back?
In the case where alpha hat is 0, yes, for a finite group. Mm-hmm.
So what I've always wanted is for that cocycle to be able to graduate density, but I don't know whether that's accurate or not. I feel like that's the
I can't, yeah, sorry, I can't say.
could be.
Good questions. Okay, so now the next step is to go into the quantum theory, and the idea here is that we're going to put a measure on the space of G bundles over a D manifold, that is the space of fields over space-time, so that we can sort of integrate out this dependence on the bundle over our space. So let's start with a definition. So let M be any old smooth manifold now. I want to define Cm to be the category where the objects are principal G bundles over M. And my morphisms are going to be, well, as you'd expect, G equivariant bundle maps. And notice that this agrees with our notation for the space of fields that I mentioned before. The other thing to note is that any morphism is invertible. It looks locally like multiplication by some group element that depends on the point in the manifold. And so we can just invert that. And then I guess definition / proposition is that if we look at the set of equivalence classes of objects in here, so objects of this category up to isomorphism in the category, this is a finite set. It's classified by Hams from pi1 into the group. And since pi1 is finitely generated for manifolds, this is finite. Okay, so now the measure is given by one divided by the number of automorphisms for some bundle over M. And notice that if two bundles are isomorphic, they have the same number of automorphisms, so mu descends to a measure on equivalence classes. Okay, for manifolds, so for manifolds with boundary, I want some extra structure so that I can define this for the d+1 manifolds. Let's see, so for ones with boundary and some fixed bundle over the boundary, we'll define a new category, CMQ, by over. The objects are going to be G bundles over M with some isomorphism from the boundary into Q. Let's see. And our morphisms, well, you guessed it, they're going to be just these morphisms in the category where we forget the data of the boundary map, but we still want these morphisms to respect this boundary data. And again, similarly, we'll define a measure on this category by dividing out by the number of automorphisms. Notice that any automorphism of p theta is going to be the identity on these boundary components. And again, this will descend to a measure on equivalence classes. This is isomorphism in the category. Okay, cool. So now we're ready to define the quantized theory. So fix a finite group, a dimension, and an appropriate co-cycle. Okay, so now I want to figure out how to assign a vector space to closed-oriented D manifolds. So first remark that we have this functor from bundles over Y to complex lines. This was given by the classical TFT. Given by and so we'll define the vector space we associate to Y to be invariant sections of this functor. let me just recall the definition from last week. Elements in the space are going to look like choices in the target objects as we run through bundles over Y that behave nicely with respect to morphisms. So if I have a bundle map, these elements agree. And now the thing I want to note is that, okay, well, we saw before that when our domain category was connected, this is either 0 or 1-dimensional, but now this space of bundles over Y is no longer connected. So this could have a larger dimension than just 1. And it's an exercise. I put this online as well to show directly from this definition that the dimension of the space you get is finite. And let me define the inner product as well. So the inner product on this vector space is given as follows. If I have two invariant sections, I will.
So you said the dimension does not have to be 1?
Correct, yeah, because this category is not connected. So look at equivalence classes of bundles over Y. And then I sum up the inner products coming from the sections, but weighted by the measure. The reason we weight this by the measure is that this is supposed to mimic the L2 norm. And so that ends up looking like integration. So that's the inner product space we associate to closed-oriented D-manifolds. For compact-oriented D+1, we'll let the vector in the boundary. OK, so this should be some sort of invariant section over the boundary. And it's given specifically by integrating the action functional over the space of fields. With respect to this measure. Let me write out more concretely what this means. So this is my sum over representatives. And it's e to the 2 pi I of the action functional scaled by the measure. Well, let's see. So this is an element of the line associated with the boundary of P. I can think about it as an element of the line associated to Q by pushing forward under this isomorphism on the boundary, so that this will actually give me a section.
There's something very natural about this measure. Why do we? Well, that's a question, not a comment.
Let's. About the measure itself, or?
Yeah.
Let's see. I imagine that, like, I mean, later, like, to actually show that this defines a TQFT, we have to prove all these measure-preserving properties. So I expect that this measure arises so that those properties hold.
What is this theta sub star mean?
Sure. So this is the isomorphism from the boundary of P to some G bundle over the boundary of X. And since we want this to be an invariant section, if I didn't have this theta sub star, this would be in the line associated with the boundary of P. And then we use functoriality from the classical TQFT to push this forward to an element of the line associated to Q.
Sorry, Tom, to make your question. So that measure we relate by the number of automorphisms, that's like the measure used to get groupoid cardinality, right?
Right. It should be like 1 over the volume of the automorphism. Like
you might just say like groupoid cardinality we know is a good thing,
Okay.
so let's use that measure.
No.
And then the big theorem is that these assignments define a TQFT. So a functor from Bordisms, now with just orientation into, well, I guess it's complex inner product spaces. And it has the usual functoriality, orientation, additivity, gluing properties. I'm not going to go through the proof of this. Just to say kind of what the sketch is, I mean, it uses the TQFT from the classical case, and then it just kind of amounts to showing that the measure behaves nicely with respect to this integration and these assignments. The real hard part is kind of the gluing property. There we need kind of a sort of technical lemma to say how the measure changes under gluing. Yeah, and then I just kind of wanted to illustrate a little example via computation.
Sorry.
Mm-hmm.
We really just lose G, like it no longer appears in.
I mean, the theory still depends on G, on the group G, yeah.
And on alpha?
Yes, and on alpha hat. Fix a group, dimension, cocycle, we get a TQFT.
Oh, okay.
Mm-hmm.
Yeah, okay.
All good?
Yep, yeah.
Yeah, so the computation I want to look at is for the untwisted theory, meaning when alpha hat is 0. So when alpha hat is 0, as we said, the lines associated, I guess this should be lines associated Q, have canonical trivializations, and the action functional just gives us 1 in the classical theory. So in this way, so now these sections can be identified with functions, complex valued functions on isomorphism classes with the L2 inner product. And these isomorphism classes of bundles over Y, they're classified by homomorphisms from pi1 into the group up to conjugation if Y is closed and connected.
Wait, what do you mean by L2?
Like the usual L2 inner product. It's kind of the proof of this exercise is showing that we can realize this as sections of a line bundle over the set of equivalence classes. And then this inner product that's defined is the L2 inner product for sections of this line bundle.
So you're defining that to be the L2 inner product.
Yeah, yeah. Mm-hmm. In other words, invariant sections become functions from Cy into complex numbers. The invariance condition forces it to just be, well, to descend to functions on equivalence classes, and this just becomes the L2 inner product of functions on equivalence classes.
So it's all finite, so these are just like functions.
Exactly, yeah. Or if you prefer, like, tuples of complex numbers indexed by equivalence classes of bundles over Y. And if we have a homomorphism from pi1 into the group, then identifying this with a bundle, the measure is 1 over the centralizer of the image. And if I've got a closed and connected D+1 manifold, the vector I associate to it should be, well, some complex number. Work through the definitions, and you get it's the sum over, well, bundles, which we can think of as equivalence classes of these homomorphisms. The measure scales everything by 1 over the number of elements in the centralizer of the image. Let's just rewrite this. All right, stop worrying about equivalence classes. And then orbit stabilizer theorem tells you that this is 1 over the size of G times the number of homomorphisms from pi1 of X into the group. And so for the case where we look at a 1 plus 1 TQFT, this is counting these surface group representations into a finite group. And that's where I wanted to end it for the first part. I think we'll take a break, and then Andrew will talk about how we can define this for surfaces with boundary.
No, don't press anything, please.
Okay. Can do. Are we live?
We are live.
All right, great. So surfaces with boundaries. So, you know, before the break, we saw that there was this functor that, you know, was going to send, it's going to be from board. So I forget the notation, something like G bundles or something. It was like that to, you know, so I think you said, is that the notation? Is that right? So, you know, I was going to send some closed guy, y, to something like e of y, I think is what we said it was.
We didn't have G bundles anymore?
Sorry?
It was more reasons without G bundles.
What do you mean?
At least in the very end, we can start.
Yeah, just oriented.
Oh, yeah. I mean, yeah, that's true. But, I mean, in the beginning, we started out defining this for,
This is the class.
yeah.
I see.
So this is without assuming that alpha hat is 0?
It's probably
Say what?
E than L. So then we had two things. One of them was L.
Right, and that was a line.
Yeah.
And then there was a
it
whole like
E.
vector space which we associated to a
And
closed
it used G
manifold.
bundles, but then we had E, which didn't use
Yeah. Okay, so let's do it that way. Okay, cool. So at any rate, you want to see what you can say about surfaces with boundary. Not fitting into this framework, but we just want to. So this was saying that a closed two-manifold was going to some complex inner product space, and then now we want to do the same thing, but for a surface with boundary, right? So to extend to surfaces with boundary, we're going to need to specify extra data on the boundary of y. In particular, we're going to need to think about pointed bundles over the circle, right? Or, maybe you have more boundary. Doesn't really matter. So, an important thing to know is that, or to notice at least, is that if you have a pointed G bundle over a circle, so G is a finite group like it was before, yeah, then that's going to have no non-trivial automorphisms that fix the base point. Right. So what this is going to do is so they say this in the paper, but it kind of rigidifies the data a little bit, and it does it gives us some extra structure that we can work with. Right. So let's let C, I want to say y prime, be the groupoid of pointed bundles, so G bundles over a surface Y with parametrized boundary, and where the point in sort of your bundle lies over a distinguished boundary point, right? So they're parameterized, so you just you know where one goes or something. And the morphisms should preserve base points, right? So if you do that setup, then kind of similar to how it was done for closed surfaces, except that you kind of do your stuff for L boundary. You can say that there's some functor from C, so I said C prime, right? Yeah, C prime. C prime Y to Ly. So this is going to be metrized complex lines like before. And it's going to send some guy Q here to something which I'll denote LQ, right? And this is going to satisfy all the sort of functoriality, additivity, stuff we said before. And should also say that this satisfies a gluing property. Basically, if say Qi over Yi are pointed sort of G bundles over surfaces with boundary, say Yi. So parametrized before, and Si are closed submanifolds of boundary of the yi's, respectively. And I also know that Q restricted to Qi restricted to Si or 1, 1. So those guys match up on those boundary parts. Then Q1 composed Q2 is a bundle over sort of glued surface, and this guy over here satisfies L Q1 tensor L Q2 is going to be isometric to L of the thing that I get when I stick them together, which I'll denote that way. Okay, so sort of key example is going to be just a cylinder, right? So by this gluing property, C, so maybe I denote this by S or something. Maybe that's confusing. Let's just say this is S. So, or no, maybe let's say C for cylinder. How about that? So the set of equivalence classes of pointed G bundles over this guy C has a groupoid structure. So maybe I have some T1 over like a cylinder sort of thing, and then similarly over here, and let's see. That's sort of a picture, and I want to glue these together. And the thing to note, I guess, is that such bundles are parameterized by the holonomy about S1 cross 0, and so the boundaries are parameterized, right? So I have some like mark point on it. So I can say that, let's see, I was using point cross 0, 1. So those are going to be some like elements of your group, right? And so we write, T X G for a bundle with this holonomy on, let's see, I was going S1 first, right? S1 cross 0, and on this sort of interval part. I think that's right. And X, G are going to be in a group or whatever, right? So if I want to glue these things together, then with this sort of notation, maybe I'll write it over here, but you can keep an eye on that picture. You can state exactly what the condition is for two of these guys to be able to be glued to one another, right? So with this notation, Tx1 say, oops, G1, composes with T of, X2, G2, say, when X2 is going to be G1, X1, G1 inverse. So maybe now is a good time for some color. I hate these scratchy chalks, but I guess that's all we have. Okay, so, stick these guys together, and So what do I want to say? Let's say that this guy is maybe like x1 like that, and then maybe, oops, let's do this in white actually. So x1 like that, and then maybe say g1 like that. So similarly here, g2. So if I'm going to stick these together, then it had better be the case that this path is the same as that makes me really uncomfortable. That path there, right? So you can think of that as being like x2 is like that yellow one, and then this guy is like that orange one. Yeah? Sorry. I'm sorry, what?
You said these cylinders are a key example. Can you repeat what they're a key example of?
So this whole sort of setup here, right? So this is just for surfaces with boundary.
Okay.
So this is a particular example of, something you can do.
Okay, so we should be thinking, so those TXD things you're describing are pointed bundles over the cylinder? Okay, so a pointed bundle, I think you said the points, it's got like one point distinguished over a boundary point, but it looks like you're talking about two boundary points on the cylinder. Like, you've got one boundary point on the left end, where that loop is coming and going from, and then you've got another boundary point distinguished on the right end, that's attached to the other end of the shape. So
wait,
do you have one distinguished point per boundary component?
Yeah.
okay. Do you also have a distinguished?
Because the whole boundary is parameterized by some number of S1s, right?
Okay. Is that path between the boundary points also distinguished, also picked out?
Yeah, it's how you get this second holonomy thing.
Okay, so I should really think of a pointed bundle as something which is, has a point over a distinguished point in every boundary and also a path between.
Sorry, could you say that again?
The path is extra. The path is extra data. Okay, but they should have a pointed bundle as having a point over every boundary. Yeah. Okay. And so that was over there, I thought you were talking about the 2-3 case, where like the boundaries are two manifolds.
Yeah, we were, but now we're not doing that sort of thing.
Okay.
I mean, we're not thinking about like 3 manifolds with corners or anything.
Okay. So if I wanted a key example in higher dimensions.
Well, we're not quite done here yet.
Okay.
And we're going to talk about this a lot more, actually. So, yeah. Hopefully we can clear things up for you. Okay, so we were going to say that, and then that's what it means for things to compose. And, oops, you can say that the glued bundle is going to be in this notation T x1 g2 g1, right? Okay, so where am I at now? I think I'm right here. Cool. Let's see. And just to note, it says similarly for equivalence classes of bundles, right? Because if you're gonna, since there's no automorphisms of these things on the boundary, then if I take an automorphism of something that's on some surface with boundary, the isomorphism class of the thing on the boundary doesn't change, so I can still glue. I don't get any funny stuff, right? And this gluing thing in this setting looks like, well, we can just write this out. So L of x1 g1 tensor L of x2 g2 is going to be the same as L of, just kind of rewriting this thing. But something you can see which will end up being important later, is that L of any old x in the identity tensored with itself is going to give you back exactly the same thing. So this sort of trivializes this particular guy. All right. Okay. Oh, and I guess I should say also, I did this for just one cylinder, but you can do all this for as many cylinders as you want, right? Any closed one-manifold crossing interval, you can run this kind of thing. And
that thing you wrote down, trivializing LXE is isomorphic to C.
maybe that verb is better. I mean, I'm just saying that like you get this thing. Okay, so a sort of brief algebraic aside about coalgebras and comodules. I have a distinct feeling that I'm probably the only person in this room who doesn't know about these things, but that's okay. It helps me. So a coalgebra, say A over C, everything we're doing is over C, is a vector space with two sort of operations on it. So it's going to be a co-multiplication. And that's just going to be some map, we'll call it delta. And it's going to be A to A tensor A. And this guy's got to be sort of, what do they say, co-associative. Meaning there's some diagram that's got to commute. Is there a bigger piece of chalk I can use? No? Maybe that one. Ooh, yeah. Good call. All right. So this is co-multiplication, and we also are going to get a co-unit. So I'll call that epsilon maybe, and that goes from A to complex numbers. And these guys have got to be, C-linear. And similarly, a an A, co-module is a vector space with something called the coaction, right? So maybe this is confusing too, but I'll call this map delta as well. It's going to send E to E tensor A, right? And then just some facts that we'll need about this setup. In finite dimensions, a coalgebra A is dual to an algebra, and the double dual is isomorphic to the original thing, as you would sort of expect. And what else do I want to say? Oh, there's another thing that I want to say. Wait, and now I've lost it. Right. So that's one thing. Second thing, an algebra is semi-simple if it is the direct product of matrix algebras. So, A is isomorphic to some product of, say, m lambdas, and this is notation that will come up later. So the lambdas are going to be in some big set called phi that indexes irreducible representations of A, right? All right, so maybe now's a good time for an example. So let's let G be a group, and so finite group like before, and then we have G acting on X, which is going to be some finite set. And where am I? So then we'll call A the complex valued functions on G is a coalgebra. So why should that be true? Well, so we need a co-multiplication. What's that going to be? So if I have some A, which is a complex valued function on this group, then we can define this sort of co-multiplication of A, which should be evaluated on, two group elements to just be A of their product. Right. Similarly, if you want to know about this co-unit, then that should probably just be, whatever value A takes on the identity in G. Right? So let's define E to be similarly complex valued functions on this guy X is going to be a comodule. So what does that look like? Well, I need to tell you what. So if phi is going to be some function in E, that sort of delta of phi should eat tensor A, probably X I, and then G, and it should just be phi of G acting on that X I. Is that right? Okay, cool. So with that in hand, we can come back to this whole cylinder business and see what this has to do with anything. Well, anyway. Okay, so just we know what we're talking about at this point. So let's go back to this Chern-Simons stuff we were talking about. We're going to follow this group, is that called a group coalgebra? Is that a fair thing to call it? Or is that a totally different thing that I'm, okay. Yeah. Cool. I'm just going to write group example and then, just, you know what I mean. Okay, we follow the group example, but on the groupoid sort of C prime S. So remember, we said S before was going to be this cylinder thing, but you might as well just think about, as many cylinders as you like. Of equivalence classes of, G bundles. Okay, so let's let E of maybe I want a disjoint union of cylinders now. But yeah, let's do that. So E of this thing here be L2 of just L2 functions on this guy. So, okay. So, and so E is supposed to, you know, recall that construction we had for closed two manifolds, but just to abbreviate it, I'm going to call it suggestively A, and then write down the theorem, which is proved in this paper, that A is a unitary. So you know it's got a inner product on it, coalgebra. So why is this true? What's the co-multiplication? Well, I have A, which is living in here, and I want to know what delta should do to it. Well, it should take in some equivalence classes of bundles over this thing, T2, and it should be A of their composition when defined, and 0 the rest of the time. Right.
Are you just picking a certain number of disjoint cylinders to work with?
It works for however many you like. Basically, what we're going to do
Like
is
one at a time for each choice of, like you could do this for 5 cylinders.
yeah,
or
totally.
more, but you're doing
Basically,
this
we're going to do it
separately.
for the number of boundary components of a compact two manifold,
Okay.
however many that is. Okay, so that's your co-multiplication. And oops, what else do we need? For the co-unit, recall that we had a trivialization of, you know, this guy. So we can define this co-unit to be A evaluated on this thing, just summed over all the x's in my group. Right? Okay. So that does that. And now, if y is a surface with parameterized boundary, we can assign a vector space, say E of y, which was going to be, you know, so we saw this kind of thing before, equivalence classes, and they take values in sort of isometry classes of these complex lines, which satisfies kind of like some stuff we saw before, or maybe the right sentences for which. Diffeomorphisms, say y to y prime, induce isometries of EY. Oops, y. So what else might you want? E of minus y is just E of y bar, and has this additivity thing. Okay.
Wait, so it says we can assign a vector space dy.
Yeah.
Is it? I don't know what it is. Am I supposed to know what it is?
Yeah, that's it. So it's L2 functions from equivalence classes of pointed G bundles over a surface with a boundary y to these complex lines that we set up before. So way at the beginning, maybe I should recall that, but way at the beginning we said there was a way to associate, to take a pointed G bundle over some surface with a boundary and give it some line. And then this is going to be a similar sort of construction where you have, so in section 2, there was this setup where we assigned a line to a particular G bundle, and then a vector space to a closed 2 manifold or D manifold or something, right? So this is a similar sort of setup, right? Now that it's not closed, it's not it's not a map to C, but it's some kind of map to lines, abstract lines. I know we didn't really go through the proof of that construction, but it's the same kind of thing. Right? L2 functions from this guy to this guy. And I guess good timing, which. And this agrees with the assignment for closed surfaces. Described earlier. Okay. And another sort of important thing here. So in addition, E of y has a right a boundary of y comodule structure, and it works in largely the way that you would imagine. So you have some so this is just for some representative, but say I have some surface with boundary like that. I don't know, maybe it's got more holes in it. And I look at this algebra that I get by looking at a bunch of cylinders, and I have some T over that guy. And I know that Q restricted to the boundary of y is going to be the same as T restricted to, 0 cross whatever you want to call that. Basically by gluing, So for any, phi, which is going to be a function in the space E of y, a bigger piece of chalk. I just need to tell you what this comodule structure is. And that's just going to be, well, largely what you would expect. So Q, T, oh, oops. So say I have right. So I want to know what that is. And you just say it's phi of Q composed T when defined or when composable, and 0 otherwise. Okay. Cool. So that was a lot of setup, I guess. But at this point, Max is going to show you what you can do with this, or an example of how there's a computation in the paper that he's going to go through that sort of is about that uses this sort of thing and all this kind of setup. But I think now is a good time to switch. If I can get this thing off.
example of this structure in practice where we calculate the SL2Z action on the inner product space associated with the torus for some arbitrary theory. So fix a finite group as before. Now your co-cycle, and I guess it's going to be C3 of the classifying space. And then, so as I mentioned before, we get a TQFT. And then as Andrew just mentioned, there's a way to extend this functor so that it's also defined for two manifolds with boundary. And these two manifolds with boundary have this, this co-module structure, and we get a co-algebra structure for the vector space associated to disjoint unions of cylinders. So I'm sure most of you have seen already the usual action of SL2Z on the torus. And so by functoriality, since this is orientation-preserving diffeomorphisms, this gives us an action on the vector space associated to the torus. And what we're going to investigate is what's the action of one of the generators. Specifically, this one. On the vector space we associate to the torus for this theory. And we're going to use these cutting and pasting properties and the extension of this functor to compute this. So, okay, so take the torus. We'll cut along a meridian to get the usual cylinder. And so since T fixes the boundary, it gives us a map of the cylinder. And I'm sure most of you have seen this before. We have some path kind of wraps around. So fix a parametrization of the boundary of the cylinder. And we're going to consider this associated groupoid of equivalence classes of pointed bundles over the circle, which, as we saw, was indexed by pairs of group elements. OK. And the vector space then, as we just saw, the vector space associated with the cylinder had this co-algebra structure. It was L2 functions, which we can think of as a bunch of lines, possibly degenerate. And this had a co-algebra structure. Let me call this space, I think we're using A of S. Let me just call this A. And the gluing property for these surfaces with boundary identifies the vector space associated to the torus as a subspace of this vector space. Namely, it's going to be the elements of this algebra that I guess behave nicely with respect to transposing the order of these groupoid elements. for all pairs in the groupoid. Now, dualizing A gives me an algebra it's finite dimensional, since I got finitely many lines. And in fact, it's also semi-simple. This is a theorem that holds for general these general coalgebras associated with a disjoint union of cylinders. But in this case, we're just thinking about it for one cylinder. And I can identify now this subspace associated with the torus as living inside the double dual. And it's the space of central functionals on the algebra A star.